All right, we've seen this function before. Well, almost. Not exactly. The only difference with this between this one and the one we've seen before is this right here. The one we saw before went to the natural numbers, not to the positive integers. Remember, z plus is the positive integers. Okay. So yeah, in an earlier video in the functions 2 lecture videos, I proved that this function, when it went to the natural numbers, when it went to the natural numbers, not the positive integers, was 1 to 1. So this one also is 1 to 1. 1 to 1-ness doesn't change by changing the target. But one thing that does change by changing the target is that now this function is also onto. Oops. Right, I don't know if you remember, but from the functions 2 lecture videos, when I did the other version of this one, it was not onto, but it was almost onto. The only thing that didn't get hit was 0. So now that I've removed 0, everything gets hit. All right. So let's go through, let's see, f of 1, 1. This is going to be 2 to the 1 minus 1 times 2 times 1 minus 1. So that's going to be 2 to the 0, which is 1, and 2 times 1, which is 2, minus 1 would be 1. So this will go to 1 there. Okay, changing this to a... So 1, 2. 1, 2. 2 to the 1 minus 1, that's still 2 to the 0 or 1. 2 times 2 is 4 minus 1, that goes to 3. So we have a 3 there. Okay. Three, 1. 3 and 1. So that's 2 squared, or 4. 3 minus 1 is 2, so that's 2 to the power of 2. So 2 squared, or 4. And over here we have a 1, so we get 4. Let's see, 4, 5. That's probably going to be pretty big, huh? Let's see what we got. 4, 5. We got 4 and 5. 5 times 2 is 10. 10 minus 1, so yeah, I'm doing this part first. 10 minus 1 is 9. 2 cubed over here, so is 8. So we get 72. All right, so when do we get 2 out? So for what? So we'll work backwards. Now, let's see, we want to get a 2 out. So what do we have to put in to get a 2 out? Let's see, we're going to want a, we're going to get, now remember this is the power of 2. This gives us powers of 2, and this is always odd. So 2 is a power of 2, obviously, and we definitely don't want an odd there. So put the 1 there. So we need a 1 there, okay? So 1 there, and then we put a 3 there. That'll be 3 minus, no, that'll still a little too big, huh? My bad, that's a little too big. What do we need? We need a 2. 2 minus 1 is 1, so that's 2 to the 1. Oh, okay, so 2, 1. 2, 1 there. And now we want to get a 5 out. So that means we definitely don't, we want 1 here, right? We want this to give us a 1, so we want a 1 there. Right, that'll give us 2 to the power of 0, that'll be a 1. So, okay, so then now, let's see, if we put a 3 there, 3 times 2 is 6, 6 minus 1 is 5. So that means we want 1, 3. Okay, like I already said, and you can just look at the table and do the thing that we always do, and that is that everything over on this side is different. Right, remember two ordered pairs are different if they have a different a different x or a different y or both. Okay, so each of those are different. There's no DNEs, so it's onto, and these are all different, so it's 1-to-1, so we know it's a bijection. This tells us that there's just as many ordered pairs of positive integers as there are just positive integers. All right, now let me just mention real fast, I would like to just talk about why it's onto a little bit. In a previous video, I proved that it was a 1-to-1. Let me just talk a little bit why we know it's onto. Okay, so take for instance, let's say the number, let's say, look at 60. Look at prime factorizations. We got 2 and 30, 2 and 15, 3 and 5. Okay, so 60 is 2 squared times 15. Or you could think of that as 3 times 5. That's perfectly fine. Now every integer, every positive integer can be written uniquely as a product of primes. That's a really important fact. It's not just that it can be written as a product of primes, but there's no other way to write it except for the order. You could write it as 3 times 2 squared times 5. That's because multiplication you can do in any order. But that's not the uniqueness part. So the order of the factors, the orders of the primes is not the uniqueness part. The uniqueness is the primes themselves. There's no other way to write 60 as a product of primes, as a multiplication of primes, as other than 2 squared times 3 times 5. Okay. So with that in mind, now let's just take an arbitrary positive integer. Let's say k is an arbitrary positive integer. Okay, now we can write k as a product of primes. So this is 2, let's say 2 to the, so 2 to the a, so the power is a, so some power 2 to the, now a could be 0, right? Let's say k was equal to 15, then a would be 0. Okay, for that one, 2 to the a times 3 to the b times 5 to the c, and so on, some amount of primes. Odd primes here. Okay, so this basically shows that why this formula works. If you can write any positive integer as a product of primes, where the first prime is 2 and 2 to some power a, and then the rest you have all the odd primes. I don't know what all the odd primes are that make up k, so I'll write p and then let's say z or something. All right, now, so what this basically shows is that every positive integer can be written as 2 to some power times an odd. Now, why can we get just an odd there? Okay, so remember that, let's see, if you square an odd, you get an odd. Well, that's true of any power. So an odd to any power gives you an odd. Okay, so this is an odd here to a power is an odd. That's an odd. That's an odd. And when you multiply odds, you get an odd. So this is going to always be an odd number. This is always going to be 2 to a power. So you can always write any positive integer as 2 to some power, a non-negative power, a natural number power, times some odd. And so that's why this formula works, and it's onto.